Hey everybody, it's me Steve. Welcome to the Geo-Files. Today what I'm going to do is I'm going to talk about a real-world example of something I've been alluding to for a while now. I've been wanting to talk about the Huronian Supergroup, but I needed to do some lean into it to get into it. Does that make sense? I don't know. But anyway, the Geo-Files episode I did on detrital zircons and stratigraphy and showing you how to confirm the laws of stratigraphy by using radiometric dating. This is going to be a real-world example of that. The Huronian Supergroup is a very interesting Precambrian Paleoproterozoic sedimentary package bound at the base and at the top by igneous rocks. It is they're about the same age. One of the first Precambrian passive margin sequences. We know at this time, around 2.5 billion with a B years ago, that modern plate tectonics, at least close to what we have now, was in action. Prior to this, it wasn't. We had a gray area extending back to about 3.2 billion years ago, and before that we still don't really know how the Earth got rid of its internal heat. It wasn't plate tectonics then. Okay, so this is the first time we have plate tectonics in the geologic record reflective of that, because passive margin sequence, basically what's being deposited, the coastal plain of the southern United States, is a passive margin sequence. On the Atlantic coast, down in the Gulf of Mexico, on the southern U.S. These are passive margin sequences. Basically, as a rift forms, which would be the mid-Atlantic rift in this case, you get a bunch of volcanics, and then as the continents move apart, you get new ocean crusts, and the continents start to shed sediment. So basically what you get is you get an igneous assemblage on the bottom, and then you start getting sedimentary rocks on top. Now this is associated with Wilson cycles. You get an ocean basin opening, but then they inevitably close. Okay, and that's the Huronian records that as well, with the Nipissing intrusions on top. But what does all this have to do with ages? Well, I needed to give you a background on the Huronian Supergroup, but before I get into that, I'm going to show you where it is located. So the Huronian Supergroup correlates with other sedimentary packages, metasedimentary packages in the Upper Peninsula of Michigan. We have, the only reason why I'm showing you these is because you're going to see them later on the correlation chart. We have the Marquette Range Supergroup and the Calco-Clay Group of the Menominee and Marquette Ranges. You see those red circles. All right, and the red box with the arrow shows you in relationship where it is to the Huronian Supergroup, which is relatively close to Lake Superior and along the north shore, essentially, of Lake Huron, with some exceptions. It does terminate near the Grenville front. Actually, it does terminate at the Grenville front in a lot of places. So these are the locations known to have what we call chronostratigraphic equivalent formations. What do I mean by chronostratigraphic equivalent? Well, I've talked about stratigraphy and lithostratigraphy, and lithostratigraphy is how we define things like our basic units in geology. In lithostratigraphy, here's my markers, we define units, we give them formal names, and the basic unit is the formation. I've talked about this stuff before. In lithostratigraphy, the key word here is lithos, rock. We use the rocks, their lithology, their physical properties, grain size, texture, that kind of thing, to classify them into formations, which can be subdivided into things like members, tongues, lenses, but they don't have to be, and we can put them in groups and supergroups. When you see geologic maps, you see lithostratigraphic units, but there are other ways to classify rocks. We can use chronostratigraphy, and I'm not going to get into hardcore details about it here because it's a lecture for another time, but I do need to touch on it. Well, I'm going to show you formations. I had to show you the lithostratigraphic because the Huronian Supergroup is a lithostratigraphic package of rocks, and it's divided into lithostratigraphic units, into groups, formations, and a couple of them are members. But anyway, chronostratigraphy deals with, like I said, time, chrono. So it deals with time. But in lithostratigraphy, a rock unit, just say sandstone, all right? We have a sandstone right here, and we'll say it's 30 meters thick, all right? Now, that's a physical thing. That's a physical thickness. However, this sandstone, if we're going to give it a chronostratigraphic time frame, we'll say we know from a lava flow here and a lava flow here that this is 950 million years old, and this is 980 million years old, the MAs. So we have 30 million years, 30 million years to deposit this sandstone. Now, although the sandstone is 30 meters thick, let's say our lava units are 60 meters and 90 meters thick. So stratigraphically, lithostratigraphically, okay, hope this is a little cleaner. All right, so lithostratigraphically, when we're talking about thicknesses, making a strat column, like I've talked about before. So this is a simplified thing. It's not meant to represent anything in particular. Relative size-wise, that's probably more like 90. We have, this is 90 meters thick, this is 30, so a third of this, and this is 60, which is 2/3 of this, or twice this thickness. So that's how we lithostratigraphically would correlate them. Now, we know that this sandstone took, well, we suspect that it might have taken the entire 30 million years to get deposited. We know these, these are actually assemblages, but we know from dates that these all are about a span of about 5 million years each. So if we were to adjust chronostratigraphically, our thickest unit is going to become our sandstone because it took the longest amount of time to be deposited. So we'll say this is our sandstone. Okay, so we have 980 MA there. I'm going to drop the MAs. All right, and 950 here. That's our sandstone. Okay, so we have that here, and now at 945, or about a sixth of that, we have one lava unit, and the same thing down here, about 1/6 of that. Sorry, this isn't, I'm eyeballing this, so it's not going to be perfect. So I'm just trying to illustrate a point, and this would be 985. So lithologically, in the earth, as it physically is on the planet, this is what our strat column would look like. But from a chronological standpoint, lava is deposited geologically really quickly, especially individual flows. So although this is 3 times thicker than this, and this is 2 times thicker than this, it took a sixth of amount of the time to be deposited as our sandstone did. So if I was going to chronostratigraphically compensate for that, 950, 960 here, 970 here, 950, 945, so my 990 would be here, my 940 would be here. See, you got your time intervals have to stay the same. Time ticks forward at a tick-tock pace. You're going to see the Huronian Supergroup from a chronostratigraphic viewpoint. I'm going to use the lithostratigraphic units, but I'm going to stretch them out or shrink them based on their time of deposition. So litho, chrono. Okay, that's done. We got that out of the way. Now we can get into the Huronian Supergroup and Chalco-Clay group. It's really nice to have some extra daylight. I've actually got the door here open, and that's the only light being let in. I had to move that box to there to block the window because we have a lot of light coming in right here. I have, because it's just me, I guess. But I just wanted to, it's February 2020, and I need to get a new cat calendar in here. I still have 2019 that's up. But we're near the end of the month here, and it's upper 40s Fahrenheit. Actually, I can tell you exactly what it is. It is actually 60 degrees Fahrenheit in here, which, if memory is serving me correctly, it's about 16 degrees centigrade. I'll correct it if I'm wrong, but it's around there. If it's within a couple degrees, I'm not going to correct it. Okay, just really quick before I start getting into the charts, and I'm going to show you an actual publication of mine that I have not yet put on the website, but I promise I will. But I'll get to that in a minute. But I just need to show you the Huronian Supergroup, because these are lithostratigraphic units. It's broken down into these 4 groups. We have volcanics and plutons on the bottom. On the top, we have the Nipissing intrusions. This is a close estimate of the Nipissing intrusions. Actually, they weren't deposited really quickly. It took a few million years. So this is more of an approximate. Down here, what we have is we have the beginning of rifting. And so right at the beginning of the Paleoproterozoic. If we look at the geologic time scale here, we're working with the Precambrian. I'm just going to show you that. And we're zooming in. And we are basically dealing with the lower part of the Paleoproterozoic. It's actually a little bit smaller than this. I just wanted to include the Osirian in there so you could see it for scale. So you can see the beginning of the Paleoproterozoic was at 2,500 million years ago, or 2.5 billion, and that's real close to when this stuff started being deposited. So we have, doing a little math, just subtracting that from that, we get about a depositional time frame of 280 million years. Now, there's other things in the Huronian supergroup that are key to what happened on Earth. Not only is this one of the first passive margin sequences, it also records the Great Oxygenation Event. I can never say that word, GOE. All right, because it contains the first red beds, and it also contains diamictite in this case, or the metamorphic version of it, which would be the Earth's oldest confirmed glacial deposits. All right, I'm not going to get into a whole snowball Earth thing. That's a rant for another time, and I have that in the works. But as someone who looks at these rocks, there was no snowball Earth during this time. Okay, I'm pretty confident of that. But we still had ice ages. We had glaciers, and the stuff in the Upper Peninsula, this would be in Ontario, we have stuff that correlates just with the Cobalt Group. Okay, this other stuff isn't here. The Huronian Supergroup consists, these are your sedimentary, the named groups are your sedimentary packages. The Elliott Lake group does include some of these volcanics and plutons at the beginning of rifting. The Nipissing, as far as I'm aware, is not actually technically included in the Huronian. This would be, the Nipissing intrusions were probably part of that Wilson cycle closing. Even though we had modern plate tectonics kind of in action then, we have a rift forming, then a Wilson cycle, we have the closing. We had that going on. So we had rifting, we had subduction, but we still had kind of a warmer lithosphere. So as the ocean basins started to close, and eventually new land masses, the Pinocchian orogeny would be one of these, would eventually close the ocean basin millions and millions of years later. But in order to move from rifting, pulling apart, to subduction, you would have had rifting, and you'd have the Huronian super, and then it would start to form under that, and you would get some volcanics that would start to come up through the Huronian. And that's probably what these are. All right. The publication I'm going to show you is of my own compilation. The sources you're going to see. This is basically it right here. Obviously, that is way too busy for any of you to see. It does have references at the bottom of it. This is just me compiling the work of others. I did do the compiling. I did not do any of this dating. All right, but you can look up the sources. I will give you the references here at the very end, which are included in there. But what is part of that are the basic lithologies present in the Huronian Supergroup. This is a close-up view of it, so you can see it a little better. And like I said, this is all in that publication, and then it's listed on top. Okay, so if we look over here, you'll see we have glacial cycle with subcycle. All right, these glacial cycles that occurred basically at the bottom of the 3 top groups of the Huronian did not persist throughout the entire Huronian. The Huronian is not a 280 million year snowball Earth. All right, that did not happen because the sediments above and below it show us that there was a warming. So we had glacial cycles, and then we had subcycles within those glacial cycles, which are more reflective to modern glacial deposits in their thickness and distribution. But anyway, that's a talk for another time. But you'll see triangles, chert, pillow lavas, that weird half C upside down. We have minor erosional or questionable unconformities. It's our unconformity symbol with a D on it. Our major erosional unconformities that we know of have the squiggly typical line. Now, we will have age of zircons in igneous units, in the igneous unit. And that is just the number plus or minus with a margin of error. We can directly date igneous rocks if they are not metamorphosed. And above that, we have, in the pink box, we have the age of our youngest detrital zircons. And if you see parentheses, that's a hydrothermal overprint, meaning we had a hydrothermal event. So why am I just putting the youngest detrital zircon ages up there? Because as I have said before, you cannot directly date sedimentary or metasedimentary rocks. What you can do is get a youngest zircon. That gives you a maximum age. You cannot be older, and I've said this before, you cannot be older than your youngest zircon, but you can be younger. Okay, and fortunately with the Huronian Supergroup we have volcanics below and above, so we can bracket this entire package. Now, in order to see if our laws of stratigraphy and our concepts of early passive margin formation are correct, all of our detrital zircons should be older than that. They can be far older than these as well, but we're just using the youngest one. So our youngest ones should all be older than the Nipissing. Okay? That is a prediction we are making. And if we see younger zircons in these rocks that are younger than that, we're going to have problems with our concept. I'll give you a quick spoiler how many times you're going to see that happen here. And remember, this is a real world example. 0. So we actually have a very good concept. Our concept of deposition, stratigraphy, dating is confirmed with the detritals that people have been getting the past 10 years or so. And it confirms our other dating methods, relative dating. Remember, this is all absolute dating. Okay, so we have our legend. And we have all of our years are going to be millions of years before present. They're all going to be MAs, not GAs, not billions. So you won't see MA after anything. You can assume it's millions of years. That's the units I'm using. The stratigraphic columns are stylized for simplicity and represent relative thickness within the Huronian. The internal formation lithologies are representative of the lithologies at a specific level within the formation. Although they appear continuous on the column, in reality, they may be thicker, thinner, or lenticular, or discontinuous. It's me expanding on that whole chronostratigraphy thing. Based on the legend I showed you, you're going to see these lithostratigraphic units. Remember, the colors represent certain types of sediments. All right. And what you can see from it is it's complicated. At the base, okay, the volcanics, when that rifting started, a continent started to pull apart there, you have numbers on the bottom of it, and I just numbered them on the chart because it was easier than trying to shrink font infinitesimally small. So what you see are the numbers there, which corresponds to actual dated plutons and stuff like that and lava units. So I'm not going to go into them in detail here, but you see them. And if you're interested, you can look at the literature on them. And then, as you can see, they all have dates. Okay. Now, you can see some are younger because plutons can intrude existing rocks. So if you get a series of volcanics deposited, in a time frame, say 10 million years, 50 million years later, you can have a pluton come up and move in. So that doesn't mess with anything. The law of original horizontality doesn't apply to intrusions anyway. So what you see here is you see a lot of hard igneous numbers. So as you can see at the top, the Nipissing is kind of a range. What you will see is you might see UTH and LTH. Those have to do with chronostratigraphic equivalents in Africa, South Africa, within the East Transvaal Basin. They're not lithostratigraphically equivalent. They are not, we can't trace a sandstone from the Huronian to South Africa, but chronostratigraphically they are equivalent. So you're going to see some of those dates as well. See, we're just trying, the reason why people are doing this is because we're trying to better understand the beginning of the Paleoproterozoic. We have a pretty firm understanding of the whole Pangea thing, okay? And we're getting close with Rodinia. Rodinia was, Pangea 300 million years ago. What you have, Rodinia, about 1 billion. It had to be assembled and broken up after that. But 2.5 billion years ago, we're still kind of up in the air on that. We have some proposed continents like Kennerland, but now we don't think there was one continent. We don't think the supercontinents or these I shouldn't say supercontinents, but the megacontinents, where you have like 85% of all land masses together, that those didn't happen until the end of the Precambrian. And they're really only Rodinia and Pangea. Before that, you might have had supercontinents, but it wasn't all clustered together. At least that's the picture that's emerging. That can change. So what you see here in the pink is you see your youngest detrital zircons within the Huronian Supergroup. Okay, and what we can do is with these youngest detrital zircons, they have margins of error. Okay, so say we have a simple package here. We have a lava, we can directly date, and say we get 2400 MA, and this lava on top, we're going to get 2300 MA. Okay, and we pull our youngest detrital zircon from here, and say we get 20, we'll just make it easy, 2350 plus or minus 5 MA. But say we have a conglomerate layer in here, just like that. And say our youngest detrital zircon in that is 2345 plus or minus 15 MA. Now we have a firm date here, we have a firm date there, so we know it's within this 100 million year bracket. We have a youngest detrital zircon from the sandstone, plus or minus 5, is about halfway in between. And we'll say it was taken from up here. Then we have this conglomerate and it was taken from here. Well, this detrital zircons are younger than this one, but that doesn't matter. It's older than this. So both of these detritals are older than this. So we don't have a problem. The only problem is our chronology. Where does that sandwich in? Because we have a 15 million year margin of error here and a 5 million here. So what you're going to see is you might see a date on the chart. You'll have 2300 here, because it is an interpretation of the dates, 2400 here, okay? See, this isn't to scale, you might see 2350 here and 2345 here, because we still have to take into account those margins of error, okay? This would be our best guess. 5 million year deposition. This could be younger than that, but just from what we know, we'll say there's a strong unconformity here, so it's probably close to the youngest, okay? So we would have something like that. So you're going to see something, you're going to be like, wait, that doesn't quite line up with what's over there, but you got to remember, you got to take the margin of error into account as well. So we form this picture using our detrital zircons and our absolute dates. We can package it a little better, okay? Now you see here on the left, what we have is we have actual numbers now. Right? So we've gone from taking those dates and actually getting numbers, and the numbers correspond with our margins of error and our detritals. We've established a time frame now, and nothing really contradicts. And we have, like in the Gordon Lake Formation, right here, we have a lava unit at 2308 plus or minus 8. We have a young detrital zircon here, 2315 plus or minus 5. So we bracket the Gordon Lake at 2309 and 2295. You can be younger than this, but you can't be older. Okay, so there's not a problem here, but we do have a firm date. But we have a margin of error, so we have to take that into account. Okay, I hope that demonstrates that a little better. And you'll see that along the chart, here and there. Now, those dates of the Huronian Supergroup that I just showed you will correlate with the Marquette, or some of the rocks of the Marquette Range Supergroup in the Upper Peninsula of Michigan, because we have detritals from those as well. The basal glacial sequences we know now, which would be like the Fern Creek Formation, correlate with the basal of the Gauganda, which is the Coleman member. It's one of the few lithostratigraphic units in the Huronian Supergroup that is divided into members, but it correlates with the Coleman member, so the glacial deposits of the Gauganda. That we've got that from the detrital zircon data. And we add our times. And as you can see, this helps us form a much better picture of the passive margin sequence that formed in the region of the two biggest Great Lakes 2.5 billion years ago. All right, so we can start to form a picture of early tectonic environments, from a rifting to a passive margin development to the closing of an ocean basin, the completion of a Wilson cycle. What I'm showing you here is a very close-up view of the Cobalt Group, the youngest of the Huronian Supergroup groups, with all the dates in tow. And at the top of it, you notice these nipissing intrusions. And you see several dates. And what does all that stuff basically mean in the nipissing intrusions that you are seeing here is that since we got better dating, we notice that they all are not, or all the nipissing intrusions, if you will. There are slight variations in lithologies. Actually, there's big variations, but basically they were not all intruded into the Huronian at the same time. They were close, but not at the same time. There are variables that margins in error cannot account for. Like, we don't have like this. We don't have 2200 plus or minus 1. We don't have 2207 plus or minus 10. We don't have 2203 plus or minus 5, where they would all overlap and we could say, yeah, they really all were the same event. We have stuff outside of that, which you can see from the chart here, which means the nipissing intrusions were pulses. And as you can see here, I've basically made the prediction that as we get more dates, because we don't have a lot of dates, not enough to confirm this, but my hypothesis basically is that there were 3 main pulses of nipissing intrusions. But that's something somebody else can work on in a master's thesis or whatever. I'm never going to tackle that. I'm just going to admit that right now. So we move along. We see we have a good zoom in of the Cobalt Group, which is the one that's equivalent over the long distances more than anything else, especially in the Upper Peninsula of Michigan. You have this glacial stuff on the bottom in green here, this G3 with subcycles G31, G32, and G33. And as you can see, even from the fact that this has been chronostratigraphically extended or shrunk accordingly, because these are actually some of the thickest deposits in the group, the Cobalt Group, and so is the Lorraine, but it actually looks thick here. But anyway, it did not take as long to deposit as we thought. All right, you can see here, this is from a paper. It is referenced. You can see that's where I got this concept of these subcycles within the main third glacial main cycle. I just wanted to show you a real world example of how we can take our previous radiometric dating concepts of geology, and the Huronian Supergroup was named long before we started pulling zircons from it, and it is a mess too. And a lot of reason for doing this is try to sort out stratigraphy, because it's fault like the Murray fault zone, the Flack Lake fault zone, because as the Huronian, it started out as a passive margin sequence. All right, it's part of Wilson cycle, so ultimately it closed. And upon that closing, that means you have an orogenic event. You have an orogeny. You turn these passive margin sediments become parts of mountain ranges. So you get a lot of faults in them and stuff. So one of the reasons of doing this is to try to figure out, what goes where in questionable areas. Because although we have formed a picture of the Huronian for a long, long time, well, back deep into the 20th century, there's still questions. There's always questions that need answering. It's never done. And you answer one thing and another question pops up. These detrital zircons do confirm our early concepts of the Huronian supergroup and the deposition of these rocks. All right, we didn't get any wacky dates in the detrital zircons. We didn't get anything younger than the Nipissing intrusions or anything like that. So it basically confirmed it, and using the margins of error, we can establish a time frame for the deposition of these sediments. And that's something that's hard to do in geology. We gave up a long time ago trying to sit there and say, except with some exceptions like carbonate deposition, that's a little different. But clastic sediments, like we'll see a thick sandstone sequence, and we've just gave up on trying to develop models saying, oh yeah, this will pump in this amount of sediment this time span, because they tend to change and they tend to not be consistent. And it just became a pain in the butt to try to establish any predictive model based off of that. These detrital zircons can help us bracket that. And although we can bracket a formation, say using detrital zircons above and below, and say we get 20 million years of possible deposition, but it can be less. Okay, and that doesn't tell us how much got deposited in a day or a week or a month. We can't know that. All we can know is that 20 million years, and we can divide it evenly if we wanted to as a guesstimate within that 20 million year window of depositional rates, but it doesn't mean that's what it is. We just know it's that 20 million year window. It was somewhere in there. So when you see people try to predict sedimentary rates off of arbitrary numbers or whatever, and I've seen engineers try to do this, that makes some erroneous assumptions, especially with clastic sediments, that the sediment input is constant of similar grain size from the same origin. And that happens consistently almost never. All right, and that part of the detrital zircon pulling is this defined source area. You can have a sandstone be deposited as a sand, okay, and you can pull zircons from there, and lithologically it won't change up through its sequence, but you'll get detrital zircons that tell you it was derived from the north, and then in the middle you might see from the east or the west. So it's not consistent. But anyway, I think I'm just going to wrap that up here. You'll see references at the end. Okay, I'll show you those to you at the very end, so you can go look them up. Most of them are open source. But anyway, I think that's it. If you have any questions or comments, please leave them below, and I hope you learned something.